By the 1910s, scientists knew atoms existed, but they had a massive problem. According to classical physics, they shouldn't. An electron orbiting a nucleus should constantly radiate energy, lose speed, and spiral inward, destroying the atom and all matter in a fraction of a second. By the late 1890s, physicists thought they had the universe completely figured out. Isaac Newton had mastered gravity and motion. James Clerk Maxwell had conquered electricity and light. The cosmic machine was solved. At least that was the assumption. There were just a few tiny, pesky loose ends left to tie up. But those loose ends weren't just minor details. They were the loose threads that, when pulled, would completely unravel reality. The first thread was a problem called the ultraviolet catastrophe. According to classical physics, an idealized heated object, a black body, should emit infinite amounts of energy at higher frequencies, like ultraviolet light. If classical physics was right, every time you turned on your toaster, it would blast you with lethal doses of X-rays and gamma rays. Obviously, that wasn't happening. The math was broken. Enter Max Planck. In 1900, he set out to fix the math. To do it, he had to make a desperate assumption that he didn't even believe himself. He suggested that energy isn't a smooth, continuous wave. Instead, it's absorbed or emitted in tiny, discrete packets. He called these packets quanti, the Latin word for how much. Planck thought this was just a mathematical trick. He had no idea he had just fired the opening shot of a revolution. If Planck was the reluctant father of quantum theory, Albert Einstein was the rogue who took it seriously. In 1905, Einstein looked at the photoelectric effect, which is the emission of electrons from a material such as metal when illuminated by electromagnetic radiation such as light, the way light knocks electrons off a piece of metal. Classical physics couldn't explain it, but Einstein used Planck's radical idea and took it a step further. Light itself isn't just a wave. It travels as a stream of localized packets of energy. We now call them photons. Suddenly, the universe was no longer a smooth, predictable clock. It was digital, it was pixelated, and as the 1920s approached, a new generation of radical thinkers would realize that the deeper you look into the fabric of reality, the weirder it gets. The universe evidently wasn't imploding. So, Danish physicist Niels Bohr stepped in with a radical quantum fix. Bohr declared that electrons are locked into fixed, allowed tracks. They can jump between these tracks, but they are forbidden from existing anywhere in between. It was the original quantum leap teleportation at the subatomic level. By the mid-1920s, a younger generation of physicists took the wheel, split into two warring camps over what electrons actually are. Werner Heisenberg looked at the math and saw pure particle mechanics. Erwin Schrödinger looked at the experiments and saw pure fluid waves. The shocking truth, they were both right. It was wave-particle duality. Matter behaves like a wave of possibilities until someone looks at it, forcing it to choose a single reality. In 1927, Heisenberg dropped a philosophical bomb, the uncertainty principle. In plain English, you can know where a particle is, or you can know where it's going. But nature strictly forbids you from knowing both at the exact same time. Schrödinger thought this was absurd. To prove how ridiculous it was, he proposed a thought experiment. Imagine a cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the poison releases, and the cat dies. If it doesn't, the cat lives, according to quantum mechanics. Until you open that box, the atom is in a superposition, both decayed and not decayed, which means, terrifyingly, the cat is simultaneously alive and dead. This was too much for Albert Einstein. He had helped start this revolution, but he hated where it landed. He despised the idea that the universe was governed by cosmic dice rolling and probability. To which Niels Bohr famously responded, "Einstein, stop telling God what to do." Einstein lost the argument. Nature, it turned out, loved playing dice. And while it sounds like science fiction, this bizarre subatomic rulebook is the foundation of our modern world. Without quantum mechanics, there are no transistors, no microchips, no computers, no internet, no smartphones. We learn to accept that at the deepest level, reality is a ghost story, and we built our future on the ghosts.